Okay, well here this exponential, this is an exponential growth equation. In the exponential growth relationship, we've got a positive sign over here by the growth constant, lambda. So otherwise it's pretty much the same form of the equation. We have n over here. This is the number of something. It could be the number of people on the planet. It could be the number of bacteria in a petri dish or something like that, but we expect to see that n increase exponentially through time. So again, kind of the flip side of the coin. And we start off at time, maybe just refer to that artificially as t equals 0. That could be today. Um, so just kind of arbitrary. It's whenever you start your observations, you have a certain number of objects, that's your n0. And then when you ask, okay, how long does it take for n to double, you're basically saying, okay, what's this time for n to become equal to 2n0? So we just run a line out on the time axis and then drop a line from the point of intersection there. And this would be our TD. That would be the doubling time, let's say. So if we usually don't know what lambda is. We don't obviously don't know what the doubling time is, but we might be able to make an observation. Let's say after 1 year, we see that the population increases, and let's just say that this is t equal 1 year. After 1 year, the population increases, let's say, by 1%. So n increases 1% in 1 year. And remember that 1% is basically 1/100th of the whole. So 1% represents a fractional increase of 0.01 n0. Okay, getting a little cramped there, but so we're saying that after 1 year, n is equal to the initial population, n0, plus 0.01 n0. Let's factor out the n0, so we can say that n then is equal to n0 times, and then we'll just have 1.01. Okay, and so n, our new value of n, is going to be equal to the starting value, n0, times e to the lambda. But now we no longer have a variable up here. We have a specific time. It's 1 year. Okay? And lambda, the units of lambda, again, sometimes you'll see a constant in the denominator. Sometimes you'll see it in the numerator. But if it's whether it's in the numerator or in the denominator, the units have to cancel out. So we know that the units of lambda are going to be the reciprocal, or 1 over a year. So notice that in this equation that we have now, that these two terms, we can divide both sides of this equation by n0. This gives us the simple relationship that 1.01 is equal to e to the lambda. And here's where you use your logarithm tricks, your logarithm skills. We know that the logarithm is kind of the inverse of the exponential process there. We want to get at the exponents. We know that the log of a number gives us the power that we have to raise the base to in order to get that number. So in this case, with base e, we would rewrite this as the natural log of 1.01 0, 1 is equal to, and then we have the natural log of e to the lambda. And we know that the natural log of e to the lambda is going to be equal to lambda. What power do you have to raise e to in order to get e? Is just going to be equal to lambda. So we have a nice simple little relationship here that we can solve directly for lambda. We just take the natural log of 1.01, and that is equal to lambda. Now you will find that for these very small numbers, that lambda will be approximately, but not exactly equal to 0.01. We'll work with that, and the problem that we're working on in class, I think you should have an easy time with it. Now the problem that you're working on goes a little bit beyond this, because you're asked to determine, once you've figured out what lambda is, you're asked to determine what n is after a time or in 50 years when t is equal to 50. So this is going to be pretty straightforward. We know that n of 50 should simply be equal to, we know what n0 is, that's given at the start, and then we know what lambda is, and we're just multiplying that by 50 and then solving for this new value. Now another question that you could be asked is, okay, what's the doubling time? We really haven't answered that question. What's the doubling time? But think about what you're asking when you ask that question. You're saying, what is the time td? What does that equal when the number n increases to 2n0? So come back to this equation, substitute for 2n0, and solve for the doubling time. Everything else would be known in this equation. You know what 2n0 is, you know what lambda is, and you would be solving in this case for td, the doubling time.